what we need to fix is how do we train smarter? How do we actually prove we're generalizing? How do we interpret all those weights? And how do we map out what those weights map to a function? Because once we can do that, we can prove when someone says this model does X, Y, and Z, we can go and analyze the weights, map it to actual circuits. We can go these neurons map to this circuit, and these neurons map to these circuits, and now we can actually look and go, okay, yeah, this lines up.
Welcome to Practical AI, everybody. My name's Jeff. I'm here with Peter Lynn. Practical AI is brought to you by Pocket AI. Pocket AI is a tool you can use to edit the weights of your model. With Pocket AI, you can prune over 60% of the weights in your model while increasing accuracy. Peter, before we get into our main topic, which is very, very technical, we wanted to just kind of circle around with sort of the fail, might call it, of the
Hmm.
OpenAI platform, both their new model and their open source model. Tell us a little bit about what the community is talking about with their model.
Yeah, so basically, looks like people are not happy with GPT-5. And originally, people tried it and people were unhappy, and then OpenAI said, "Oh no, no, no! It's because there was a bug in the UI. It wasn't actually using GPT-5, and supposedly they fixed it." But even after they fixed it, people were kind of unhappy and were asking them to go back to the previous version, and they said, "No, no, no, no! You can just select the older version." So basically, people don't really like it. Is the punchline. The open source community has been playing with the open source version, and most people are kind of laughing at Sam's quote saying that like you can run the large one on your laptop. Well, not really, because unless you have a H100 or really high end video card, you can't run it. And his quote that you can run the small one on your phone is not really true either. So basically, people are just calling him out.
Yeah, even Wall Street Journal is reporting that the five rollout is pretty rocky. That people are requesting to go back to four. Um,
Yeah.
and then on the open source side, you were saying that they can't run the small model on a phone like they thought they could, and some of that's been
Well, in
rock.
theory, if you want it to just process one token a second,
Okay.
right?
So
I
that,
mean, like if you're going to wait a good 15 minutes for a reasonable prompt response, sure, you can run on a phone.
yeah,
I'm impatient. If it's not running like 60 to 300 tokens per second, I'm not gonna bother to use it.
yeah, it's a waste of time at that point.
Yeah.
Okay, let's move on to a very technical topic, and it has to do with fusing um, of attention layers and stuff. But ultimately, the punchline here is that attention is expensive, but also you might argue that the attention architecture is not the architecture of the future. Explain a little bit for the technical person kind of how you've come to this conclusion.
So I think before we dive into that, it's good to know the history of what attention was meant to solve. So originally, when neural networks were created, they had no memory. And so then someone came up with this idea of let's add memory to neural networks. And one of the popular ones was called LSTM, long short term memory. And the idea was you would remember what things are important so that you could figure out which things you need to learn, right, to attend to. So the problem with that is you have to process things sequentially again and again and again. And so it was really slow. The Google researchers said, okay, well, let's speed this up. So they said, let's take text, randomly remove words, tell it to predict the word that we took out, and then they used this attention mechanism, which is basically memory, to remember the relationship between words so they can figure out grammar and syntax and so on. And so the attention has a couple parts. It has a query, a key, and a value, and then it has a bias for each one of those. And the real benefit is that you can then now distribute the training on thousands of GPUs and it's much, much faster, right? LSTMs were slow to do the same amount of training. It would take you anywhere from 10 to 100 times longer. So, for example, OpenAI spends 16 to 18 months to train a new model. So you just multiply that by 10, right? Like, it's going to take you 10 years to get the same result. So it's not
Yeah.
really practical.
And then over time, that's almost 100 years now with where they're going.
Exactly.
Yeah, okay.
Right. So it was a huge advancement, and that's great. So it's shown us what is possible. But ultimately, in my mind, it's a wrong architecture because one, the models are all over parameterized because you've got these attention layers. So there's this problem called the quadratic problem, where it takes 4 times more memory because you've got all these attention layers. So clearly, if you want this to scale, you need to remove that. You need to find so we need to learn from what attention does, and then we need to figure out a better mechanism or technique or framework or something that can do the same thing but not require that much memory and that much processing.
And you like to analyze the parameters themselves, and one of the exercises that you've been doing over the last couple of weeks is you took I think it was a TIM model that had fused
Yeah.
the attention layer in with the rest of the parameters, and in order to run the analysis that you wanted to run, you've decided to unfuse that. Explain a little bit like what you're doing and why you're doing it.
So fusing just means that so normally the attention layers, the query key and the value are separate arrays, and then when it does the math, the matrix math, it takes those arrays and it does the math. Well, how do you shorten that? How do you speed it up? Well, if you take the queries, keys, and values and make it into one array, well, now it's one set of operations instead of three sets of operation. But you're also losing the bias because now you've only got one bias for the whole entire thing. It's not three separate biases. And so you are trading off something in terms of being able to figure out things better because if you have individual attentions um, arrays, the query key and value, and biases for each one of those, then you can figure out, in theory, no one knows for sure and no one's really proven it, but if you have separate biases for each one of those, in theory, you should arrive at a better generalization in huge air quotes.
Okay. So essentially, in an effort to make a model smaller, so like for edge computing or something like that, um, an idea has been to do this fuse, make it
Yep.
smaller. The trade-off is that it's harder for you to do the analysis on to get to generalization ultimately, right?
Yep.
Okay. And this goes all the way back to you think that everything we're doing is beneficial, but it's not going to be the long-term solution. The all this.
No, in my mind, Transformers was a necessary step, but it's not the ultimate step.
Do you have any idea where this, what the ultimate step will be, or the next step will be?
No, but I'm positive that we had to do this step and blow all these gigawatts of power and build out of all these data centers to learn from our mistakes. And then once we learn from our mistakes, we'll build something better.
Okay. And but you do think that the parameters themselves will survive the
I
weight.
believe that the parameters are over parameterized right now.
But those the future architectures will have something to do with weights slash parameters, but
Right.
it
So
won't
I think
necessarily be
fundamentally
attention.
neural networks is a good architecture. What we need to fix is how do we train smarter? How do we actually prove we're generalizing? How do we interpret all those weights? And how do we map out what those weights map to a function? Because once we can do that, we can prove when someone says this model does X, Y, and Z, we can go in, analyze the weights, map it to actual circuits. We can go these neurons map to this circuit, and these neurons map to these circuits. And now we can actually look and go, okay, yeah, this lines up. Right now we can.
Got it. Well, it's fun to know where the future is, and even though we don't know what it necessarily looks like, we know it's not here.
No, it's not here. Yeah,
Okay.
no.
Good. Well, then that's from that sense, it's just fun to keep an eye on all the rest of the people that are trying weird, wacky stuff to
Yeah.
see which one of these things might be a good idea. And We probably don't even know what it is yet. Might not
No,
even.
we definitely don't, and that's why I think open source will win. Because when you're a corporation and you've got one CEO saying you got to do it because we have to ship a new release every 6 months. Are you gonna try some crazy idea? Probably not, because the CEO expects you to deliver something every 6 months. You gotta put out a release, and if you don't, then goes your bonus. So it's like, what are you gonna do?
Yeah. Well, I couldn't said it better myself. Well, it'll be fun to watch, and we'll be here for it. I know that. Uh, Peter, thank you. This is a good topic, and it's fun to get a little bit technical from time to time. You can follow us on Spotify as well. Remember that. Some people are enjoying just listening to this more than watching it. And remember, always watch us on 2x speed because Peter and I talk slowly. Leave comments, questions, we'll answer them. Until then, we'll see you next time. Take care.